So this is our logger. It's based on a simple 7-inch display that was purchased from Amazon. It's just an HDMI display that's powered by a USB. On the back side, we've 3D printed this black base that simply supports all the different components. There's a case here, of course, for the Raspberry Pi. Plugged into the Raspberry Pi, you can see, of course, a dongle that's for the mouse and keyboard that we use to control it. The flash drive, where we can just take the data from the Pi, put it onto my laptop to run with McLaren Atlas. In the bottom corner, of course, is the power supply for the display. And then this corner goes to the dongle, to the GPS dongle. The issue we found, though, was that when we originally double-sided taped the dongle directly to this back plate, interference from the Pi itself actually was causing interference so that it couldn't get a GPS lock. So what we did was we simply took a twist tie from a bag of bread and put a couple of magnets on the back so that the dongle would be able to be stored nicely, but also we can untwist this, put it out to its full length, and mount it to a section on the car, which in this case we just used the frame of the seat so that it wouldn't move. Other than that, it is powered with cigarette lighter outlet power supply for 2 amps. The nice thing, though, with this is that if we wanted to, we could also use a battery power supply that supplies at least 2 amps of current. Other than that, that's a very simple overview of the actual logger, the code itself. I wrote modifying Mac's original code, simply bringing it up to the syntax specifications for Python 3, which allowed us to use the current, or most current, version of the Raspbian OS. We are doing a track walk. We've essentially made our own miniaturized version of Martinsville, where the light pole next to the minivan there was the first set of corners, and then turning back around, the second set of corners was marked at where the parking spots end. We, of course, were very careful not to hit any vehicles, but that is the track that we are using for our data logging. This is an overview of the track map, which we were able to create by plotting the latitude and longitude against one another as the X and Y in Excel.
The car today that we are using to test our data logging on is a 2014 Scion FRS, and the mods we have under it, it's just a regular old catback, nothing much. Changed the intake filter, but that's all. Besides that, it's completely stock.
So there were 4 runs performed. The first was a baseline with traction control and VSC on. The first run, VSC, or vehicle stability control, was disabled. The second run after the baseline, the traction control was disabled. And then the third run, passenger, being me, was added to the car, and it was reverted back to VSC being on and traction control being on. So Kevin, tell me about the differences you felt in the vehicle as the driver from the baseline to each of the 3 different runs.
So with the first one where we had the VSC, the vehicle stability control on, I felt that the car could potentially push a little bit more power. However, it still felt limited in a way, such as if it lost a little bit of traction, it kind of cut a little bit of power. Moving to the second run, we had the traction control completely off, as where when the rear started to slip a little bit, even though it had lost some traction, it still allowed for me to continue pushing power when the car was completely sideways, and almost as there's no limitation. And lastly, with Brayden in the car, comparing baseline with him in the car, there was almost no difference due to how slow the car was moving. The difference was not noticeable.
So we've now taken the data that was exported from the Raspberry Pi and put it into McLaren's Atlas software, where we can do an analysis of the data itself on a plot. So the very top plot here is the speed of the vehicle in miles per hour. The second plot down is the altitude of the vehicle. Third down is latitude, then longitude, and the track parameter. So looking at this, you can see that generally over the course of the run, it is the red line that is faster. So you could see that the comparison here is the baseline is the blue line, and the first run, which is where we turned off vehicle stability control, is the red line. And so you can see over the overall course of the lap, they're pretty similar, but the vehicle overall over the course of the lap was faster when vehicle stability control was disabled. Now, this could be due to one of 2 reasons. One being that with vehicle stability control turned on, the vehicle automatically reduces power when it detects that traction is being lost. Meaning, in the baseline run, when Kevin would have stepped on the throttle a little bit harder, especially coming out of the corners, the vehicle would reduce the power in order to reduce wheel slip as part of the vehicle stability control in the electronics of the vehicle. And so you can see that where these reductions in speed are, especially in the red line, which again is that lap 1 or run 1 comparison, the drop-off from the highest speed to the lowest speed is actually quite a bit more pronounced, and you could see that the increase is also more pronounced. So on the baseline run, the vehicle stability control is trying to make it so that the vehicle is accelerating smoothly, whereas Kevin, with his right foot, is trying to make it accelerate as fast as it possibly can. So now we are looking at the comparison between the baseline and the second run, where we disabled traction control. Again, this is compared to the baseline, so the blue line, in this case, once again, is the baseline, the red line is our comparison lap. So looking especially at the miles per hour, the speed of the vehicle, you can see once again that compared to the baseline, the difference, the delta, from the highest speed to the lowest speed is much more pronounced. That deceleration and acceleration is happening at a much faster rate. Now, granted, with traction control off, there's a much higher likelihood that in a racing scenario, Kevin, when he puts his foot down, may be more likely to actually spin the car out when he goes to hit the throttle, goes to get on the throttle with traction control disabled. But you can see over the course of the lap, generally that maximum speed, that Vmax, is quite a bit higher with the traction control disabled, once again because the car isn't reducing power when he gets onto the throttle to prevent him from losing control. So now we are finally looking at the comparison between the baseline, the blue line, and our third one, the red line, which had myself as the passenger. Now, what's interesting for this run is that it very much appears to be in line with what the driver Kevin suggested in his feedback at the end of the run, where he said he felt very little difference between that and the baseline with myself as the passenger. This is backed up pretty significantly when you look at especially the speed of the vehicle, and you look at the slope of deceleration and acceleration. Now, they're not perfectly 100% lined up, but you could still see those slopes are much more similar than they were in comparison to Run 1 and Run 2 when VSC and tractor control were turned off. This also lends to the fact that the driver is the most important piece of measurement equipment in the car, because his feedback indicated to us what we now can confirm with the data that we recorded. So overall, this shows that using even just a simple piece of equipment that cost less than $100 to put together and to make and to code, we were able to get very valuable data that backed up our driver's feedback, even in a very simple setting using just a parking lot. But it was indicative of the power of this technology and how it can be used in a motorsports application at scale simply by using just a GPS sensor. And that could be even further augmented with more sensors such as wheel speed sensors, gear sensors, and other data taken directly from a vehicle's ECM.